Hello and welcome everyone to today's webinar, which is brought to you by Thermo Scientific in partnership with Azo Materials, and is titled "How the New ARL iSpark Plus Metal Analyzer Can Streamline Your Lab Workflow by Taking Speed and Stability to the Next Level." A big thank you to the team at Thermo for making today's event possible, and to everyone in the audience for joining us from across the world. My name is Danny from Azom, and I'm delighted to be hosting today's event for you all. I'd first like to introduce today's fantastic speakers and then explain a little bit about the format for today's event. So, firstly, I'm delighted to welcome Wilhelm Sanders, Product Manager at Thermo Fisher Scientific. Wilhelm studied physical engineering at the Rheinische Academy in Cologne, where he gained his first experience with optical emission spectrometers, which also ignited his passion for this particular technology. Since then, for more than 30 years, Wilhelm has worked in this field for various companies and roles, first in applications, then in automation, and later in service and sales, and finally as product manager. Since 2021, Wilhelm is working in his role with Thermo Fisher Scientific as the task of developing high resolution, high end spark spectrometers really has appealed to him. What he likes about this particular role is that it enables him to have close contact with his customers and interact with research and development as well. And joining Wilhelm is Jean-Marc Bolin, Products Applications Manager at Thermo Fisher Scientific. Jean-Marc holds a master's degree in chemistry and a PhD in NMR spectroscopy from the University of Lausanne. He joined the optical emission marketing team at Thermo Fisher Scientific in Écublens, Switzerland, 23 years ago. After many years as application manager and product manager for OES, he's currently product applications manager, responsible, among other things, for applications of the inclusion analysis and collaborations with partners in the metallurgical industry. A big welcome to you both. Today's webinar will run as three parts. In just a moment, Wilhelm will start off with a 30-minute presentation before handing things over to Jean-Marc. We'll then move things into an audience Q&A. So if you have any questions at any stage, then please write them in the Q&A box, which you'll find on the right-hand side of your screen, and we will answer as many as we can following the presentation today. Quick note that if you are watching this back on demand, then you can still ask your questions at any time, but you'll receive a reply to your question via email. Finally, before we get started, the webinar is being recorded and we will share the link with you via email within the next 24 hours. So please do share that email with anyone else you feel would benefit from watching today's content. And you can, of course, watch back on demand anything that you miss today. Right, let's get things started with the presentation.
Thank you, Danny, for the introduction. Hello and welcome to this webinar about the recently launched new ARL iSpark Plus series. My name is Willem Sanders. I am the OES product manager, and today my colleague Jean-Marc Bolin, as product applications manager, and me are going to explain how the new ARL iSpark Plus metal analyzer can streamline your lab workflow by taking speed and stability to the next level. First, I like to give you a brief introduction how Spark OES works. Then I will explain why and how the ARL iSpark Plus instrument series is meeting highest requirements for analytical needs and how its user-friendliness contributes for simplifying your day-to-day routine work if you need to analyze metals and expecting the highest level of trustable results. Jean-Marc Bohn will then explain how you can benefit from another great unique feature of the instruments, the determination of non-metallic inclusions. We will end with a conclusion and have left some time for your questions. OES is the workhorse for elemental analysis of solid metal samples since many years. It is widely used in the complete cycle of metal production, metal processing, and recycling. In OES, atoms are excited. Excitation energy comes from a spark formed between a sample and an electrode. The energy of the spark causes the electrons in the sample to emit light. The light range used for Spark OS is in the visible and ultraviolet range of the electromagnetic spectrum. Especially the UV range requires special attention since this light is absorbed in ambient air. All this light is then, via the spectrometer, converted into spectral pattern. By measuring the intensity of the peaks in this spectrum, indicated here, the analyzer can produce qualitative and, via a calibration with certified reference materials, quantitative analysis for your measured unknown samples. Some words about the new iSpark Plus. It is based on the ARL iSpark series. It's replacing all the same models, the 8820s with fixed configurations, the 8860 version where you can specify your element and matrix selections tailor-made, the inclusion analyzer models FE1 and FE2, and finally the special fire assay analyzer. As said, based on the previous ARL iSpark models, it comes with important improvements. The thermal stabilization, we have a new patented spark stand design. It has improved shutter system, and also we improved the communication between the spectrometer software and the instrument for faster analysis. Let's see why and how these new important improvements of the ARL iSpark Plus supports you in your routine workflow. Let's have a look what is important regarding the parameters for an OS influencing the workflow in a laboratory, first from the analytical performance parameters point of view. There are elemental coverage, low detection limits, good accuracy, high precision, long-term stability, which means high availability for you, and fast results. We will also talk about other parameters like software user-friendliness, maintenance, easy to be done, and optional software tools. On these slides, I will present you how the ARL iSpark Plus excels in any aspect of those. First, the elemental coverage. The ARL iSpark Plus can cover 14 routine matrices marked in orange, 7 special matrices, and 5 potential matrices. It can cover almost all elements from the periodic table, except the noble gases and unstable heavy radioactive elements, and it can cover the wavelength range from around 120 to 780 nanometers. Just an example, the best oxygen line for Spark OES is around 130 nanometers, while an important element in aluminum lithium line is located at around 670 nanometers. The main contributor for this is the optics and more important, its design. A little background here. Spark optical emission creates very line-rich spectra. For example, only the iron atom emits above 8,000 lines in the spectral range I just mentioned. This is great for the elemental coverage, but requires excellent resolution of the instrument to create optimum dispersion of this line-rich spectra to separate line peaks. So the spectrometer can also be seen as the heart of the analyzer. With its 1 meter focal length, it's the largest on the market, and it's set up in Paschenrunge for the highest resolution. Resolution can be achieved with different parameters, but due to our long-lasting experience, the focal length is the optimum for ultimate dispersion and isolation of spectral peaks. As UV light is absorbed in ambient air, we use vacuum since this technology ensures not only highest transparency at any time and low maintenance and low cost of ownership, but ensures also that parameters like pressure and temperature, which might have huge influence onto the dispersion and the stability, can be kept ultra constant, resulting in great stability. Since optical fibers and mirrors tend to degrade due to photochemical effects, we use a direct view to the plasma created in the spark stand for maximum light throughput, and the heavy temperature-controlled cast iron spectrometer for high stability, even now with improved thermal stabilization, equalizes directly ambient temperature changes. So our optical solutions provide superior resolution and performance for all elements and matrices. Low detection limits. Why are low detection limits being important and become even more important with the transition of the metals industries towards the reduction of CO2 emissions? Well, scrap and recycled metals as a resource are getting more important for this transition. The problem which occurs here is that scrap is likely to be contaminated and maybe not well sorted. Elements which are not wanted or cannot be removed during the melting processes, for example, tin and copper in steel, may enter the process. To avoid this, lowest detection limits are of utmost importance to monitor this closely. Another reason is that requirements for high purity metals like pure copper are increasing as well. What means limit of detection? The limit of detection, LOD or DL, is the lowest possible concentration at which the method can detect, but not quantify. The analyte within the matrix with certain degree of confidence. It is also defined as a lowest concentration that can be separated from a background noise with some reliability. The LOD is also influencing tremendously the LOQ, that is the range from which you can measure with some high level of accuracy. Thermo Fisher Scientific is one of the few Spark OES manufacturers, if not the only one, who guarantees those detection limits for all offered applications. Let's take a closer look which parts of the instrument contributing to those ultra-low detection limits. Again, here a huge contributor is the spectrometer itself. Because as mentioned before, to get clear, sharp, separated peaks resolution is a must, but also the detectors and the readout system and how you proceed data acquisition plays a key role here. For our high-resolution spectrometer, the ARL iSpark Plus, we are using exclusively hand-selected phototubes, and this with a good reason. For each photomultiplier tube channel or PMT, we use programmable high voltage setting which allows optimum settings for every application and element, guaranteeing optimum conditions for working ranges and avoiding saturation. The PMT is able to perform what we can call TGA, time-gated acquisition. Some other call it time-resolved spectroscopy. And this can be done with every PMT channel. Each channel can have its specific optimum window for detecting the optimum part of the signal. Why is this important for the detection limit and the performance? Well, this is the biggest advantage of a phototube over any other detector technology existing. For example, solid state detectors. A PMT has the capacity to be read out ultra fast. And as mentioned earlier, in OES we have line-rich spectra. One reason for this is the fact that we excite atoms, and during the excitation there's also a recombination of ions creating a lot of emissions, which create a kind of optical background noise and also interferences. However, at the end of the excitation signals and even after the plasma extinguishes, those ion lines are not emitting while atoms still do. If your detector and readout system can be triggered to process signals only from this short moment, you will improve drastically the signal to noise ratio, which leads to extremely improved detection limits. Furthermore, this window is element dependent. That means, in best case, your detector and readout system should be able to set these windows and that element specific. Up to today, again, this element specific optimum TGA window settings are only possible with phototubes. This leads to the fact that the Thermo Fisher Scientific ARL iSpark Plus, with its high resolution 1 meter focal length and phototube detector, can achieve lowest and guaranteed detection limits for most elements and matrices. Additionally, we do a dark current electronic offset subtraction, which also improves the signal to noise ratio. But there's another great benefit of phototubes, which is a single spark acquisition possibility. Single spark signals can be acquired individually and not being integrated to allow special data treatments. Some can be used for improving accuracy and precision, which I will explain a little bit later, but also you can use it to calculate soluble and insoluble concentration and inclusion properties with SparkDat. This will be explained in detail by Jean-Marc a little bit later. Here we have visualized on how we can set TGA windows per element channel. The signal is only integrated during a well-defined time window and repeated at the frequency of the single sparks. The benefit is we can only select here the best part of the signal where the noise is at minimum and can also suppress interferences. By doing this, we improve tremendously, as said, the detection limit. So this window can be set per element optimum, and thus we receive lowest detection limits to suppress this background noise and interferences. Some examples we can see here that this window is element specific, while, for example, arsenic is best in this delay and window time. For example, chrome is working better and showing better results for detection limit at another stage. Good accuracy and high precision. You all may know this graphic explaining the difference between accuracy and precision. So precision means how close the measurements are to each other. What we have stated earlier for the detection limits, it's also valid for the precision. We guarantee those. Here are the detection limits, and for the precision, we guarantee per element and working range for any element to be analyzed in a matrix. Accuracy is how close a given set of measurements are to their true value or reference value. The achievable accuracy of a Spark OS depends on the quality of the reference material used for the calibration and that of their certification, and on some instrumental attributes and parameters as well, as mentioned the optical resolution, spark source conditions, or the TGA windows. For precision and accuracy, next to the components already discussed, the excitation source and the methods of signal acquisition and processing plays a key role here. Our IntelliSource is a very innovative spark source for OES. This double current control source helps our specialists design efficient spark current shapes for sample surface preparation, material ablation, light emission in each metal matrix by optimized pre-integration, which minimizes the effects of both the matrix and metallurgical structure. We can optimally remelting and homogenizing the sample before integration, and we can do perfectly integration current shapes, which are delivering optimum performance both for elementals in trace concentrations and major alloys concentration. Already mentioned, with the ability of the phototube reading signals reading out very fast and single spark acquisition, we can also set up special algorithms which can support even precision and accuracy. One is called FAST, which stands for Flexible Acquisition Start Stop, which allows processing the optimum subset of single spark intensities. Sometimes it needs quite a while to get stable results, and we can just filter out with this technology and see only and take only in consideration the good part of the signal. Another smart data processing form which improves the precision and the accuracy is called DESIRE. It stands for Diffuse Spark Intensity Removal. It can discard abnormal low intensity signals which can occur during erratic behavior of the plasma and the spark, which can be created by metallurgical structure defects inclusions that ends in low signals of the internal standard, and we can detect this with this single spark acquisition and also suppress this part of the data, only taking again the good part of the signal into consideration. Again, this drastically improves accuracy and precision. Final word about the accuracy. Since OES is not an absolute measurement technology, the instrument can only provide quantitative results via a calibration with reference material. Each ARL iSpark Plus metal analyzer is individually calibrated by hand in our factory. The calibrations are performed using many CRMs. The calibration curves are established with a powerful multivariable regression tool, which corrects for matrix effects as well as spectral interferences and ensures the highest possible accuracy. On top of this, the calibration is verified with rigorous quality tests to ensure meeting your demanding application and specifications. This includes a detailed calibration, accuracy validation, and certification. Stability. Stability of the instrument is of utmost importance when performing routine analysis. High stability reduces the frequency of maintenance and drift correction operations. It will increase the availability for the instrument for routine analysis of process and production samples. This parameter is important if the sample load is high and results are required extremely quickly, for example in steel process control. For this important parameter, we have put a lot of effort during the evolution of the iSpark Plus. Let's see what we have improved on the iSpark Plus series. One part we improved is the thermal stabilization of the optics. Here we improved the airflow and ventilation, but also the oven regulation algorithm to react faster on ambient temperature changes. The result, significant improvements in the long-term stability, even if ambient temperature is changing quite fast. We have also implemented a new shutter system, which is improved for full protection of phototubes against over-illumination during high-energy pre-spark, also leading to higher stability. But the highest contributor is the new patented spark-stand design. We have here introduced an additional double argon channel to increase argon flow and create turbulences to increase cleaning intervals and stability. This is only applied at the end of the analysis phase and leads to a reduction of dust by 45% and increases the maintenance intervals for 30%. It has also a strong effect on improving the long stability feature, and it leads also virtually to no memory effect. Let's have a closer look here. I plotted some examples. So here what you see is we did long-term stability test over 4 consecutive days. We did run a series of samples and did more than 3 to 4,000 burns in these tests without any standardization in between. What you can see here is first very tight limits, example carbon in low alloy steel, and no trend to drift. Same for nitrogen over days, another important element in low alloy steel. Other examples I plotted is carbon in cast iron. Also here again, no drift, flat lines. And finally, for iron and steel, I plotted another example, very important element in stainless steel, nickel, which is one of the most expensive elements to alloy. And to keep this stable and reliable results will save you a lot of money. Same we did for aluminum. Here I picked some examples for 2000 aluminum series for copper. Again, no drift to see. And for silicon alloys, the 4000 series at a level of 7%. Also stable, tight results. As a side effect, we could also see from the use of the new improved spark stand that we could eliminate the, in OES, very well-known memory effect. I'm now over 30 years in OS and I have seen this effect so far on any instrument. What is the memory effect? So in this case here, we have sparked first a stainless steel and then a ultra low carbon steel, and expected value was for chromium 63 ppm and for nickel 32 ppm. What happens is that the deposit in the spark chamber of the previous sample will be picked up in the plasma and showing higher results than expected for the following pure sample. Typically, you can overcome this if you burn a depollution sample, a pure or blank sample from the matrix, in this case, a pure iron sample, several times, up to 4, 5, 6 times, and then you get the expected results on your pure sample. This is taking time, and with the new ARL iSpark Plus and the improved spark stand, we don't see this effect at all. Right directly, the first results after these high concentration samples, we get the expected values on the pure sample, either in automation or in manual brushing mode. Same we see in aluminum. Here we sparked first high silicon at 7%, and the expected low alloy or pure sample we sparked after this one was at 15 to 20 ppm. And again, with the iSpark Plus, we don't see this typical memory effect. That is saving you a lot of time when switching from alloys to pure metals. Fast results. As mentioned, we could also improve the communication between the spectrometer software and the instrument's firmware, and that was leading to a reduction of the measurement time per run by 15%. Just an example, in the past, analysis for low alloy steel took us 21 seconds, including nitrogen. Now it's less than 18 seconds, which makes us to one of the fastest results deliverer in our instrument in the range of top high resolution spark spectrometers. Performance will not be influenced. So here I've summarized some benefits. I took an example of an electric arc furnace steel plant, but you can take also and transfer it to your application. Overall, the increased systems availability allows you to have less often standardization, less operator interference is required. You have also longer lifetime of the setting up samples, which is reducing the cost of ownership of your spectrometer. With the faster results, you can potentially reduce, for example, the tap-to-tap time at an electric arc furnace steel plant. The time saving contributes not only to energy saving, but also to reduction of CO2 emissions. And also it supports downtime avoidance. You can also do potentially more heats and have faster return on investments. I made a little calculation based on average European price per energy. You can do when only 1 minute saving, you can save on a yearly basis more than 225 kilo US dollars. And I took another example discussing with a customer a real case. They have one electric arc furnace. They do 24 batches a day, 8.5 samples per batches, and they do around 2 to 3 runs. Making a long story short, this customer confirmed me that it is possible at least to do one batch a month more, which could mean a very fast return on investment, of course, depending on the type of steel and capacity produced per batch. If you have more EAF furnaces and more samples, the ratio can be even higher. Okay, that was it for the analytical performance parameters. Let's have a look what is important regarding the other parameters, the user-friendliness, easy maintenance, and the mentioned optional software tools. The problem today for many laboratories is resources of lab personnel is limited, and so you may need to make your software easy and user-friendly to use. Since Oxas is the most complete spectrometer software I'm aware of and is offering a lot of tools and features which can simplify your workflow, and since there are that many, I focus on a few. Some examples here. One is the synoptic panel, which is a graphic diagnostic tool showing you the status of the spectrometer at a glance. So you can see the status of the oven, the pump, also pressure of argon is okay, power distribution, everything. And it helps you during, in the rare case of troubleshooting, to diagnose and get help from service. Another one is a maintenance management system, which is using a traffic light system, indicating if the state is green, no maintenance operation needed. If orange, maintenance operation will have to be done, and red, it is due. Another nice tool is the Easy Oxas. It's the idle tool for the unexperienced operator for simplified routine operation, only having function for the day-to-day routine, such as assigning the sample ID, averaging results, and transmitting them, while the lab manager can still switch to the full Oxas for editing templates for printouts, certificates, modifying the method, extending calibrations, etc. Another interesting feature which is unique with Thermo Fisher and OES is the availability to show directly the measurement uncertainty. This is important for those of you which needs to report according to ISO 17025. I just want to highlight here that we have done last year a webinar with ISO networks, and it's still available. So I really recommend to watch this webinar if you want to have more details. It's really helping you displaying directly measurement uncertainty data with the analysis. For maintenance, I pick the most recent maintenance task, which is cleaning the spark stand, even if you can do thousands of burns depending on the matrix to analyze. This is the most frequent maintenance task you need to do. And here you don't need any tools, and it's really done it's a question of minutes. So there's also no risk to lose those tools. So it's very easy and simplified work and can be done in minutes. Optional software tools. One I really like to highlight here, and this is also a contributor for Spark that later, Jean-Marc will also pick this up, I guess, is SBC. SBC is also important for those of you which are in need to supply quality control on high demands like automotive or aerospace. SPC can give you control limits, trends, warning for your process, and also can give you information about the capability. But it's also a nice tool for audits uh, because you can also store results of your control samples to demonstrate and make audits safe to show that the instrument is working in proper conditions. Another one is total materia. That is for those of you interesting which need to also validate with help of the elemental composition a grade. So this database is containing, I would say, all the grades existing on this nice planet. And those of you who have edited already grade data tables entering grade specification limits manually know that this can be a very hard task. And with this additional software option, you can just by a few clicks can add seamless and faultless the grades you need to verify very easily and faultless. And with this, I like to hand over to Jean-Marc, who will tell you another benefit of the ARL iSpark Plus, which is unique, the Spark that and how to maximize the value of the iSpark Plus.
Thank you, Vili. Let's now talk about inclusion analysis with SparkDat, and let's see how it helps maximize the value of the ARL iSpark Plus. Today, we essentially talk about inclusions in steel. As you know, inclusions are small particles of various compositions, sizes, and shapes embedded in the steel matrix. You have a few examples in the pictures. They cause problems of steel quality. They can have detrimental effect on the properties of the finished steel, and they can cause failures of product made of steel. They also disturb the manufacturing process. For example, they can cause nozzle clogging. You have an example of nozzle clogged by aluminum oxide inclusion on the right side of the slide. So all these generate cost, of course. These costs is due to bad heat, waste, customer complaints. In steel plants, the cost is up to hundreds of thousands of dollars a year. Therefore, having inclusion under control during the steel making is key for efficient production of modern steel. The ARL iSpark Plus allows for ultra-fast check of non-metallic micro-inclusion with the SparkDat methods that have been available for more than 25 years with the ARL spectrometers. Some highlights of the methods are SparkDat transforms the instrument in a two-in-one analyzer. The inclusion analysis is combined with the elemental analysis. Analysis time is not increased by performing combined analysis. It means that in steel, you need less than 1 minute for two-run low alloy steel analysis. Instrument operation and maintenance are unchanged, and the instrument is easy to use as a normal OES. Usual sample preparation method can be used also. In other words, milling, if you use milling, or in some cases, paper grinding. SparkDat is a low-cost investment. So what are the benefits of this? You have low-cost solutions on your spectrometers that enable huge savings and, of course, fast instrument payback. You get rich inclusion data, which is available close to real time in up to hundreds of samples per day. SparkDat is therefore an inclusion analysis that offers unique solutions to have inclusions under control during the steel making. Let's see how SparkDat works. Consider 2,000 single spark performed in a few seconds. That's what we normally do in all the optical emission analysis in order to excite the element and light emission. This single spark caused the emission of 2,000 light pulses that are characteristic of the elements present at their point of impact on the sample. Then these light pulses are converted by the spectrometer into 2,000 electrical signals on each element channel. That's what we can see on this run chart. They all show 2,000 single spark signals for different elements like aluminum, calcium, magnesium, or sulfur. Let's now have a closer look at these signals. On the screen, you can see the run chart of aluminum single spark signals in a low alloy steel sample. On this chart, the peaks are due to inclusions that contain aluminum. The background signal is due to the aluminum in the metallic form, what we call sometimes the soluble aluminum. The large peak corresponds to large inclusion and the small peak to small inclusions. If we now also have a look at the calcium single spark signals, we observe two different cases. On the left side of the screen, we observe an aluminum peak, but no calcium peak in coincidence. The inclusion contains aluminum, but no calcium, and it is likely an aluminum oxide. In the second case, on the right side, we have a peak on the aluminum channel in coincidence with a calcium peak. This means that the inclusion contains aluminum and calcium, and likely it is a calcium aluminate. In conclusion, the single spark signals contain information on number, type, and size of the inclusions. In OAS, we have seen we generate single spark signals. In the standard OES analysis, elemental analysis, these single spark signals are averaged, and then via calibration curves, the concentrations are calculated. For inclusion analysis, the single spark signals are used as raw and processed via algorithm to generate the inclusion data. How does a combined analysis look like? The results are a mix of the standard elemental concentrations and the inclusion parameters calculated with the SparkDat algorithm from the single spark signal run charts. We obtain a variety of inclusion parameters instantly together with the concentration. These parameters can be handled exactly like the concentration, for example, displayed, printed, and stored, but very important, they can also be transmitted to SPC. You can see on the right side a SPC run chart of aluminum oxides, where for one of the sample, the upper specification limit, the number of aluminum oxide is too high for the sample to be compliant. Let's see now what are the main inclusion parameters we can determine. First, we have the standard parameters. These parameters are calculated only by using the single spark signals. We obtain peak counts typically and peak coincidence counts, which give number of inclusion in number per cubic millimeter. The second type of parameters are the advanced inclusion parameters. Those are calculated with the single spark signals and extra parameters like the elemental concentrations or the density of the inclusions. Examples of these parameters are inclusion-specific insoluble concentration of an element, which is the mass percent of an element due to its presence in a specific inclusion type, the equivalent spherical diameter, ESD, or the size in micrometer of the inclusion, the inclusion volume fraction, the fraction of the steel volume corresponding to a specific type of inclusion, and last but not least, the oxygen content, which is calculated from the contents of the various types of oxygen-bearing inclusions. Let's now see some examples. The samples used for this are 3 samples from voestalpine in Linz. VRM 22 and 28 are from 2 steels treated with calcium, while VRM 28 is from low alloy steel obtained without calcium treatment. You can see the aluminum, calcium, magnesium, and sulfur run charts corresponding to these 3 samples. And you can observe visually some differences in the inclusion contents of the samples. Much better with the algorithm, you can have a look at peak counts to determine number of aluminum bearing inclusion, calcium bearing inclusion, and so on. You can count total number of inclusions, the tot in the table, or you can also count the number of small, medium, and large inclusion, the SML lines. With that very simple experiment, we see that the calcium-treated steel samples, VRM 22 and 27, have significantly more calcium-bearing inclusion than the other sample. This is actually what we can expect after calcium treatment. With peak coincidence count, we can get high specificity on the inclusion type. Before, we talked about aluminum-bearing inclusion, calcium-bearing inclusion. Now we can look at aluminum oxides, calcium aluminates, or spinels. The specificity is obtained by checking not only the peak coincidences, which elements are present in the inclusion, but also non-coincidences corresponding to elements which are checked to be absent from the inclusion. This example shows that the calcium-treated steel samples have less aluminum oxides and more inclusion with aluminum and calcium. This is a confirmation of what we've seen before, and actually this is what we expect from calcium addition. On this slide, you can see an evaluation of some advanced inclusion parameters, namely inclusion-specific insoluble aluminum concentration, sizes, and volume fraction of some inclusions like aluminum oxides, calcium aluminates. Again, these parameters confirm that the calcium-treated steel contain less aluminum oxides and have more inclusion with aluminum and calcium. You can see that from the insoluble concentration and from the volume fraction of the different type of inclusions. Very important is the determination of the oxygen content. For many companies producing high-quality steel grades, it is of utmost importance to know the oxygen content very rapidly. Most SPARC OES instruments cannot measure accurately the oxygen at the requested low concentration, typically less than 40 ppm, as you can see on the table on the right side. This is because most of the spectrometers have a limit of detection for oxygen that is larger than 10 to 20 ppm, which means that the limit of quantification is normally higher than 30 to 60 ppm. A solution is therefore to use SPARC-DAT method to calculate the oxygen content from the oxide inclusions that are measured via the more sensitive elements, aluminum, calcium, magnesium, and other oxide elements. An example measured in the 3 VRM samples. On the first line, you have the result of the SPARC-DAT method. On the second line, you have a reference from company voestalpine with a similar method. And on the third line, you have a reference from combustion analysis performed during a European project on inclusion analysis. You have the reference of the project below. In the second example, we determine the oxygen content in some CRMs, AIRM samples, 5 samples, all with oxygen content below 30 ppm and certified. And as you can see with our method, we have very good agreement with the certified values. The conclusion is that with aluminum killed steels, there is an outstanding match with the reference value, which is possible down to a few ppms. And very important, it means that Spark OES can replace combustion analysis even at a few ppm oxygen content. According to experienced European steelmakers, those who took part to this European project, the most important benefits of using SparkDat inclusion analysis during steelmaking are obtained at secondary metallurgy, where it helps take fast corrective action, for example, adjust the calcium addition, at continuous casting, where it gives early warning indicator of problems like nozzle clogging, or on the finished product, where it corresponds to a fast and economical quality control of the finished product. Some concluding remarks. SparkDat inclusion analysis maximizes the value of the ARL iSpark Plus. With low cost investment, you can have huge savings. It measures inclusion during the elemental analysis, allowing close to real-time control of inclusion during the steel production, or measuring inclusion in hundreds of samples per day. It is important to mention that it is perfectly suited for use with an automated ARL iSpark. And finally, I did not talk about other matrices, but this is because we have the most experience and the largest number of users in steel. However, SparkDat inclusion analysis is also used in other metallurgical industries such as aluminum, lead, and fine precious metals. And to finish, do you want to try SparkDat on your sample? If so, contact Thermo Fisher local sales representative and make your own idea about inclusion analysis. So that's the end of my presentation, and I hand it now back over to Vidi for the conclusion.
Thank you, Jean-Marc. Well, let's wrap up with the conclusion. With reliable and fast analysis providing wide elemental range, lowest detection limits to ensure non-presence of unwanted tramp elements, and determination of impurities in pure metals, and excellent analytical performance for precision, accuracy, and stability, leading to less standardizations, less maintenance intervals, the faster analysis time, and as just mentioned by Jean-Marc, the advantages of the SparkDat for the simultaneous analysis of inclusion next to the elemental composition. The ARL iSpark Plus series, as stated earlier, excels in any aspect of the discussed parameters and is thus the ideal choice for the melt process control with the potential to produce more heats in the same time, as well as the verification of incoming materials for high demand QC and QA requirements. The ARL iSpark Plus series, due to its high reliability and low maintenance requirements, can be ideally integrated in our own automations, which we offer in different configurations. With its optional capability to determine ultra-fast and simultaneously non-metallic inclusion in many types of metals, it becomes a two-in-one analyzer, ensuring a smooth process and excellent final product quality and properties. ARL iSpark Plus, in short words, the trusted standard in OES. And this is the end of our presentation. Thank you very much for joining. And now we have time for your questions.
All right. Thank you very much, Jean-Marc. Thank you very much, Wilhelm. We, as I just mentioned, we are about to start the Q&A. So if you have any questions for either of them, then please do send those in the right-hand side of your screen, and we'll get to as many as we can in the next 10 minutes or so. A couple of notes just before we start that. As we mentioned in the introduction, the link to the recording will be sent out to everyone within the next 24 hours or so. So please do forward that on to anyone in your company who might also benefit from watching the presentation. You can, of course, watch back anything that you've missed as well. On the left-hand side of your screen, you'll find the handout section. Wilhelm mentioned a previous webinar we've done. There's a link to that in there, as well as some other resources for you to download. So please do take a look at that before you finish today. Okay, gentlemen, let's start the Q&A. Wilhelm, if I come to you first, this question is saying that they were very impressed with the memory effect elimination. You've shown examples for steel and aluminium. Is it also working that efficient for other matrices as well?
Yeah, first I have to say I was impressed myself when I saw it the first time. We have currently tested only for aluminium and iron matrix, but we're currently testing for other matrices, and we expect that it will be similar for other applications, but we're still in the testing phase. But really, we're very optimistic that it has same benefits for other matrices like copper, titanium, nickel, etc. Yeah.
Perfect. And then Jean-Marc will bring you in. Could you tell us what the main differences are between the SparkDat inclusion analysis and an inclusion analysis technique like SEM or EDX?
Okay, thank you for the question. I think it's a main question that I receive. So not simple to answer quickly, so I will focus on 4 differences. First, by the dimensionality of the method. If you have SEM ADX instrument, you have a 2-dimensional type of analysis, while with SparkDat, the analysis is over 3 dimensions. We ablate material, and then we look also for inclusion in the depth of the sample. The second difference is that the SEM ADX is able to analyze composition, shape, and also location of the inclusion over the surface. All that is not possible with the Spark OES. So we can get a composition of inclusion, but not individually like a SEM ADX. And it's not possible to estimate to evaluate the shape and the location of the inclusions. Another big difference is the time of analysis and also the sample preparation, which makes the Spark OES very fast method. We like to call it ultra-fast inclusion analysis, and the SEM ADX, which is quite longer depending on how you proceed and experience. Sample polishing is also needed compared to milling or paper grinding. That's a big difference. And the last one I would like to mention is the number of samples you can analyze. So with SparkDat inclusion analysis, all the samples you normally analyze in your process, which means for some of you up to hundreds of samples a day, you can have some inclusion analysis data, which I think with a SEM EDX for good users, you are limited to a few tens of samples over 24 hours. So that's, there are several other differences, and also with Spark OES, there are differences if you look at some type or some other type of inclusions. But I prefer to handle that according to the cases, to the different matrices and different critical inclusions you might have.
Yes, the next one's a bit of a follow-up to that. I think they're just asking, is the one that is better or more useful than the other?
Yeah, probably the 2 of them are better than the other. So, SEM EDX is probably the reference today for inclusion analysis. OES is not. The norms are made for the surface techniques, not for Spark OES. Otherwise, what could I say? Of course, optical emission is extremely fast, and that's probably the main reason to use it. And which means at the end, probably for exhaustive and perfect result, you need the microscope, and for fast analysis and control in the production, you need the OES. So conclusion, probably they are complementary and one cannot replace the other one.
Okay. Willy, we'll bring you back in. This question came in, I think it was on slide 24 of your presentation.
Okay.
They're asking, is the carbon analysis made of a certified sample or a foundry sample?
Okay. First, I'd like to greet you, Cor. That question was from you. We know each other. It's an honor for me to have such an expert from cast iron or tempered cast iron in the webinar. I have to say this sample was setting up sample, but we wanted to show the long-term stability over time, and that then is I think it's fair to use a kind of sample like this. We did also tests on production samples, but not for the long-term stability, just to see best parameters for excitation and things like that. For the long-term stability, we tested with the setting up standard. I hope this is answering your question.
Perfect. Another question from the same person, this time for Jean-Marc. Will the SparkDat analysis also work for cast iron, assuming 100% white solidified sample?
So we don't have many requests, but I'm sure there are reasons to try it and probably use it. The thing is, how you can see inclusions with the Spark OES depends on the composition of the matrix, and all depends on which type of inclusion you want to see. If you tell me I want to see about it's not inclusion, but about the type of carbon particles in the cast iron, I think that's a very ambitious problem. But now, if you have microparticles that have a composition that is very different from the matrix and with, let's say, reasonable size, typically from 1 micron to 10 or 15 micrometers, you have a good chance to observe the inclusions. I'm happy to test for you if you have samples. Actually, I know the importance of cast iron industry, and I'm really interested of working on that with somebody who is interested and convinced that there are problems with inclusion also in cast iron. You know, when I said we have less experience with non-ferrous metal, it's also the case of cast iron. So I think steel makers, especially fabricators or producers of special steel, they have noticed very early years ago that inclusions are extremely critical. I see now a change also in aluminum and in different matrices. I mentioned precious metals, also in copper. I know there are inclusions. All is about what you do, what is the application of the metal, if mechanical properties which are influenced by inclusion are critical. So if somebody in cast iron industry tells me, yes, we have critical inclusion, I just say, please send samples and we'll make tests.
Yeah, and if anyone wants to get in touch with the team at Thermo, within the handout section, you can find contact details in which to do so. So as a reminder, do download those before you leave the webinar today. We're getting pretty close to the end of the hour, but we'll try to get through a few more questions. This next one is just asking calibration required for inclusion analyzing. That's a statement / question. Any thoughts, gents?
No, there is no calibration, so we don't use... actually, I mentioned the advanced parameters, inclusion parameters, and I said we don't use only the data from the single spark signal. One parameter we also might use is the concentration of the elements in the bulk. So that's almost natural because we perform the inclusion analysis together with the elemental analysis, and then this parameter is there. So the calibration is only for the elemental analysis, and for the SparkDat inclusion analysis, we use any parameter which can help, but no special calibration.
Perfect. And then, Willy, we've got another question here for you. Does no memory effect mean users do not need to change electrodes when they switch to a different matrix?
Oh, That's an interesting one. Not really thought about this yet, but it's a good one. We still recommend, if you're changing the matrix, I guess the question is when you, for example, if you have a spectrometer which is able to analyze like iron and steel and also aluminium, if you change from one matrix to another, I would still recommend to change electrode and also the spark stand plate. But maybe we should test this. We haven't tested this, but I think that's a good idea. It's inspiring us. Maybe we should test this. Good idea. Yes. Yeah, we'll take this up. But still, for now, we recommending changing the electrode, the cleaning brush, and the spark stand plate, and to clean entirely the spark stand before switching the matrix. But I will pick this up, and maybe we can make some tests.
Yeah, perfect. We are at the hour now, so if you do have to drop off the call, just a reminder to download any resources before you do leave. There's also a survey that will appear on your screen, so if you could share your feedback, then that would be great as well. A few more questions, guys. This one's asking, with the improved stability that was discussed, what is the new recommended frequency for performing drift correction standardization for aluminium 6XXX series? How does this compare to the previous ARL models?
Well, I always, when it comes to this question, how often a spectrometer needs to be standardized, I always say I would trigger that by running reference material or control samples, put tolerances around them, and that should trigger the point of standardization. However, I know people are tending to do it based on a calendar or days. I would say we can expect weeks in between. But again, the scientific method to know when a spectrometer needs to be standardized is to run control samples to be sure when it's the right moment to do that. But for sure, compared to the previous model, it has been terrifically elongated, the interval.
Superb. And then we just got one final one here. So in ductile iron, we are facing different inclusions like CAS or MgO and MgS. That's, I think, a bit of a statement on one of the previous questions.
Yeah.
Any thoughts there?
So if I see these elements, so what I can say again, in the case the particles are of reasonable size, and if these elements present in the inclusion are not in, let's say, concentration that is too high in the matrix, there is a good chance we can see at least cerium, sulfur, magnesium. Oxygen, of course, the limit of detection of oxygen is higher, and we don't always see the peaks, but for the other elements, if we are not in the case where the percentage or the ppms of these elements is too high in the matrix, we have good chance.
Superb stuff. I think that pretty much wraps up the questions, guys. So we'll finish things up there. A big thank you to the both of you for sharing your time, expertise with everyone. Thank you to everyone in the audience for joining us live. Most people have stayed until the very end, so a big thank you. Thank you to yourselves. Final reminders that a link with the recording will be in your inboxes in the next 24 hours. Please share your feedback in the survey that will be appearing on your screen in just a moment. And don't forget to download those resources before you leave the webinar today. Big thank you again. Wish you all a pleasant rest of the day and hopefully see you all again very soon.
Thank you, Danny, for hosting us.
Thank you, everybody.
And everybody for joining, of course. Bye-bye.